and also startups. Today, she's one of the co-founder and CTO at Eoliann. Eoliann is a young Italian startup at the interface of artificial intelligence and Earth observation, and she will tell us more about it later. So in today's talk, Chiara will share, let's say, her experience, the interface of AI and Earth observation, but also as a software developer and entrepreneur. She's going to share her journey from data science to the Earth observation field and to also co-found a startup. She will also tell us about the practical application of AI in Earth observation. And I think during the talk, we will also discover, she will also tell us about popular libraries and tools in Python, PyTorch, or whatever that are useful in the field of Earth observation and to process data coming from satellite. So welcome again to everybody, especially to Chiara, and go ahead.
Okay, I will share. Yeah, can you confirm you are seeing the presentation title?
Yes.
Okay. So thank you, Cristiano, for the introduction. Thank you for inviting me. Thank you to everyone here that want to know more and is interested about Earth observation data. So let me start by saying that, as Cristiano said in this introduction about my experience, I actually am a data scientist, and I had a general experience. I was able to do some computer vision, some NLP, and this thanks to my experience in the data science startup where I worked between 2019 and 2020. So given that working in a startup gave me so much experience in a short amount of time, I decided to also found one last year, and I will speak about it a bit later. But when I started 1 year ago, I had some knowledge about Python, machine learning, and deep learning, but I didn't have a lot of experience in Earth observation and geospatial data. So the way I prepared the presentation of today is a bit like what I wanted to know last year when I started with the Earth observation. And if anybody had taken the time to prepare these kind of slides and explain me about how to best use Python with Earth observation, then I would have I would have been able to start much quicker. So I hope my slides would be useful for you. So the way I divided my presentation is into 3 chapters. The first chapter will be about what you can use, what is the toolkit for a Python enthusiast that wants to work with geospatial and Earth observation data. Second part will be about specifically AI applied to the Earth observation industry. And final part, I will tell you more about my startup and my experience. So, Python in Earth observation. I want to quickly touch on the coordinate reference systems, libraries and softwares, and finally describe you the huge amount and variety of satellite data and their specifics. So, first thing when you work with the geographical data, you have to remember you are using a coordinate reference system. We've been using the Mercator projection from a Flemish geographer of the 16th century up until today. He had this great idea of kind of unfolding the world into a Cartesian projection. And so even today, when you give your address to a friend on Google Maps on the app on your smartphone, maybe you are using the latitude and longitude, which we all know. But you don't know that its corresponding code is 4326. So next time you use the geospatial data with Python, maybe you look at the attribute of the CRS and you will find out it's in 4326. But you should never, never compute a distance with this coordinate reference system because it's geographical, but it doesn't respect the distances on the Earth. Probably you already know this, that countries closer to the equator will appear smaller than they are because the countries at higher latitudes are enlarged. So in order to compute real life distances, you need to use something, a coordinate reference system that is projected. So for example, when you work in Europe, you might use the 3035, which is, and you can compute distances in meters. Or if you want to be even more precise, you can use the universal transverse or Mercator, which are small slices for the north and for the south hemisphere. They are divided. And as you can see from the image of the example of Paris, they only range on a small set of longitudes. So, and they are coded with 5 digits. So you get to know all of these fancy numbers once you start working with the geospatial data. So, second ingredient, libraries. Most of you being enthusiastic Python users and machine learning practitioners, I know you must be using pandas. Everyone loves pandas. And you might be very happy to know that there is a geospatial correspondent which is called GeoPandas. But I want to warn you on the fact that while pandas at the time I prepared these slides is already at version 1.5, GeoPandas is still at version 0.12. So just a warning, when you use it, keep in mind that it's not as tested and as developed as pandas. Jokes apart, how was GeoPandas created? It was basically the union between Shapely library and pandas, where Shapely is a library to manipulate geometric objects, and the data is still saved in a vector format. So maybe if you are familiar with web development, this is the kind of SVG images that you use on websites that you can scale. While if you want to work with arrays, so raster images like the JPEGs or PNG, so you are using a set of pixels for each tile of the world, of the geographical location you're analyzing. You might use XArray library or raster.io, where the difference is that XArray doesn't use GDAL, while raster.io is the wrapper for Python of GDAL, which is a library that is very widespread for C language. Another set of softwares that I really want to tell you about are the GIS, the Geographic Information System softwares, where ArcGIS is the state of the art, but it's closed source, so you have to pay to use it. While QGIS is very widespread in the field of environmental engineers because it's open source, so it's free. And GraphGIS is also worth mentioning because on the website they explicitly showcase its Python API and integration. So, of course, I mentioned arrays. As you might imagine, the Earth observation data, geospatial data, it's a huge amount of data. You are usually dealing with very big data sets, very large images. And for example, the library Xarray is already integrated with Dask for parallel computation. So you will be in need of a powerful compute. Who else can come to our rescue than the almighty cloud services? Of course, they are there. We have AWS, Google Earth Engine, and Azure. They are all offering services for storage, for computation. So in the image, I put an example of an AWS architecture where you can have different pieces that are dealing with storing and processing, and they are all integrated with geospatial capabilities. Of course, I don't want to promote AWS in any way. I'm just listing the different options, and I encourage you to use the one that you prefer. And then I wanted to mention these more vertical services, because while cloud computing and serverless are kind of general purpose from the first three, we also have a Sentinel Hub, which is a service that both provides satellite data and the cloud computation service, while SpaceSense is a French startup offering a library that allows you to gather satellite data and then run machine learning or artificial intelligence pipeline with that. And now, what about satellite data? We know how to deal with them in coding, but what are they about? Probably you already know that they are not only about visible images. A satellite is not only a camera taking pictures of the Earth. They have a multispectral sensors, so it's not only red, green, and blue channels, but you have infrared imaging as well. Then, depending on the sensors that the satellite is equipped with, you get different types of signals. So, for example, ultraviolet is used to study the atmosphere in the chemistry composition of air, while you can get to the Earth's surface with synthetic aperture radar. That is particularly useful because it goes through the clouds. Because if you limit your Earth observation to optical imaging, then every time there is a cloud over what you're observing, you will lose information. While the kind of signals that go through the weather are best to give information about the state of the surface. So here there is a list of the satellites of the Sentinel mission, which is one of the missions of the European Space Agency. So each satellite has been equipped with different sensors. And of course, this was just an example, because there are a lot of missions and satellites from the NASA and the ESA. So just don't think that anything I show you is complete. Indeed, another information that you might be curious about is the resolution and the revisit time. So as I said, European Space Agency has made Sentinel satellite data open and available, so you can see that those are free of charge in these plot representations. And Landsat are the ones that are free and open from NASA. And as you can see, since they are free, they are also the ones with the coarser resolution and with the higher revisit time. So Landsat is about 10 every 10 days. They will revisit the same place on Earth, and Sentinel a bit less than a week. So this is still quite enough sampling time for a lot of purposes, a lot of applications. But if you are willing to pay, you can get, for example, Worldview, which is the very best, where those private providers are giving us a resolution under 1 meter, which means you can even see single people in the picture, and a revisit time of around 1 day or even less. So the possibilities are really a lot, especially at the higher tiers. And finally, about the data that you find for your Earth observation application, I want to remind you that they have different types of processing. So you can also find the raw data, but for the purposes, let's say for machine learning purposes, I think you're not usually doing much with them. Usually you will go directly to the pre-processed data because they have been geometrically corrected, considering that the satellite is passing over a round surface. And also you will find the ones that I decided to call derived data sets, which means those will not be specifically the result of a sensor, of a satellite sensor passing over the Earth, but they are the result of some kind of processing. For example, the digital elevation model starts from the surface elevation sensors, and the star imaging that is mapping the altitude of each point of the Earth's surface. And then it is able to build a full digital elevation model of the Earth. So when you download it, you are not downloading the output of a satellite sensor, but actually an elaboration. Same goes for land use and land cover. Land use is basically an image segmentation made all over the world that will give you the type of terrain you're observing. For example, you can say this part of land is being used for constructions, for buildings, residentials, or this can be agriculture. This other is forest, and so on. So originally, the satellite sensor has not collected the classification of the Earth, but the fact that it was all processed and made available into a land use data set makes it a kind of derivation of Earth observation data set. And the last one I want to mention is normalized different water index, which is derived from infrared non-visible spectrum. So it gives us the health of trees and crops because they retain water in their leaves. in the next slide, I give you an example of the different levels that you would find for the preprocessing of the Earth observation data. This example is specifically taken from Sentinel, but you find some similar levels also for Landsat and so on. So if you were going only onto at level 0, you will get more or less what you get from the satellite, and then they apply radiometric correction, etc. They resample. So if you want to get a more refined version and usable Earth observation data, you are very likely to go to the storage where the level A, B, or C, level 1, A, B, or C are made available. Okay, now that I give you this overview of the data, let's jump into the applications and AI, which is probably even more fascinating. So, for this part, I want to start with a metaphor. I hope you can follow me. Everyone who had experience with the early stage of mobile phones maybe was familiar with those models. So we can divide the history of mobile phones into 3 stages. The first was just you can call from wherever you are because it's a mobile phone. Then they started adding some hardware and software, so they enabled the short messaging service, or they would put the infrared port or the Bluetooth, and you could exchange files with your friends. And then at some point, they put the camera on the phone. It was mind-blowing, but usually you would just buy your mobile phone and keep it as it was, like factory settings, up until the end of its life. But then there was a revolution because mobile phones became smartphones, and smartphones are equipped with a set of hardware. You don't really bother about the fact that there is a gyroscope and the accelerometer, but you maybe only think about the fact that there is a battery and at some point it will die. But every different smartphone has a story of its own because we install different applications, and the application developers, they don't really care about the hardware, but they will program application with a programming language, and they make their applications available that can run on different devices. So all of this is to say that the space agencies are trying to do the same with satellites. Still, we aren't at phase 3, but we already passed the phase 1. We are more or less in phase 2. Basically, at first, the satellites were launched as a mobile phone in the sky to make a call to Earth and pass some information. And everybody was very happy. And then now that a huge amount of information can be sent down to the Earth, we can apply algorithms and process those data, but we are, of course, limited by the type of sensor that was mounted onto the satellite when it was launched. So funny thing is, for example, that Landsat, one of the old ones, is traveling in the sky with one of its sensors broken. So you will receive images which are incomplete, but we cannot do much more now. The sensor is broken, the rest of the satellite is flying. Okay. So the latest developments want to make satellites a bit more like smartphones. If there was some missions like PSAT-1, the orbit, that launched a big computational unit with a set of small satellites the set of small satellites will be able to perform edge computing thanks to specific chips. There is even an open challenge online. I encourage you to visit the website because there is a full of ideas for applications that can run on the satellites. So imagine the near future where there will be application developers for satellites, and the satellites can run the program on the edge. And when this kind of mission is not relevant anymore, we can stop this kind of computation and program the satellite to perform a different kind of computation, like a different application on a smartphone. I think this is very cool. So please follow the talk until the end and don't go visit the other websites from ESA. Then let's go into AI. I know a lot of you must be familiar, maybe fell in love with deep learning thanks to computer vision. So once I started preparing this presentation, I went to Jeremy Howard article of last summer, where he compares the vision models fine-tuned on planet dataset from Kaggle. By the way, Jeremy Howard is a professor. First, he was in US and then in Australia, and leading the course on Fast AI, an open source library based on PyTorch. So he prepared those comparison tables where he used the big vision models and smaller ones, which of course are optimized for lower memory usage. And he compares how you can fine-tune the typical computer vision model that was pre-trained on ImageNet onto the Earth observation images. Of course, the best performers are the new architecture, vision transformer, etc. But it's very interesting that among the small models, so optimized performance, we still get ResNet, ResNet 18, which is it will be soon 10 years old. I find it interesting, but we shouldn't do fine-tuning on natural images from ImageNet because, as you know, there is a problem of domain domain shift. So then in this next slide, I listed some papers that explain the importance of having a pre-trained model to be used for fine-tuning that were specifically pre-trained on satellite data. As an example, I put the table here that compares how when you use a model pre-trained on ImageNet, you can get a lower performance in the accuracy compared to the model pre-trained on actual remote sensing data. And the interesting thing is that you don't have to be limited to RGB channels because remember, in satellite data we have all the other we have multispectral data. So this is called RGBN because it includes infrared data. And so building on this, the probably most interesting part of working with satellite data is its multi-dimension. You have multidimensionality, you have many sensors, you have many scales, and you have the revisit time, which allows you to treat your data as time series. So even European Space Agency uses the term data cube because starting from the 2 dimensions of the world view, then you can gain a third dimension in time. And then when you multiply it by all the different sensors and physical measurement that you can do, you can get like 4 dimensions or some or more. And as an example, here we have the multispectral data set that is called Sant TS. Or you can prove that the flood inundation is improved when you use data from different satellites and you add the DEM, so the digital elevation model that I told you before. Or even some researchers at the European Space Agency are investigating the use of visual question answering models on the remote sensing data. So the possibilities are really endless. You should only be limited by your creativity. And I think as a former biomedical engineer, I want to add that in a lot of fields of data science, we are limited by the possibility of collecting data, acquiring high quality data. For example, in the biomedical field, maybe you have to convince a person to wear a health monitoring device, and you want to record the heart rate and so on, while Earth is kind of a very good patient because Earth is just staying there rotating, and we put all the satellites we wanted around it. We measure everything in time, and this is kind of the amazement part for data science. So I also prepared this slide from the full stuff by ESA. If you want to visit the website when I finish this talk, you will find these different applications. So land use, as I mentioned earlier, and then fire monitoring, etc. And they also provide the data set, the dataset and the notebooks, so you can test anything you are curious about, as well as visiting the list of their publications that I briefly mentioned in the previous slides, but you can find many others. So, yeah, so for the last part of my talk, I think more or less in time, I just wanted to touch on the experience of working and founding a startup. So let me first explain what is the idea behind our startup. Eoliann started from the observation of the fact that a lot of businesses are losing a lot of money because of the damage from natural events, natural catastrophes, which are all due to climate change and urbanization. So if a typical business of an insurance is to just measure some statistics about the damage done by natural events, the traditional modeling cannot work anymore if you don't add some, if you don't add to the computation the impact of climate change and urbanization. So this was a problem that led to loss of money. The second part of our idea was that actually we have a source of data which is scalable, is widely available, and with a good frequency. And it has different tiers, of course, of resolution and frequency depending on the free and the pay for data. So the satellites provide us with a lot of information, but we need to convert this physical, weather-related, and all these pieces of information into something that is valuable for the decision maker, depending on their own industry. So in insurance, banks, and other businesses that are interested in the climate risk for their assets, they cannot go directly to the output of Earth observation data. So given this challenge, we decided to become the conjunction ring between the satellite data and the assessment of natural events in the interest of businesses. So starting from this data and other sources, we aggregate and process them and run into a model that we train in a way to provide a probability and impact to businesses. And all of this is served in the form of an API. So the clients ask, given the location of their assets, ask for a measure of the climate risk. So given this ambitious plan, what I want to share about this experience and this journey is that you cannot treat it as my next publication in Nature. Even if it's an ambitious idea, when you work in a startup, you want to remember to proceed in small steps. So even in our case, since the focus was to deliver value to the customer in subsequent iterations, you have to remember that you want to start, for example, with a small data set, like a small set of locations. And then we started with hydrological and physics-based computations. And then we add even more improvements one at a time. You should never be anxious to put everything together because because complexity adds up very quickly. So then you turn some experiments into binary classifications, and then you assess the improvement, and then you turn your experiment into regression, and then you assess the results, and then you collect more features. And so you kind of do an ablation study, but instead of compiling a table for your paper, you're actually gathering insight on what works best for your product. So that is my take-home message. If you want to lead a team into the development of software based on AI, remember to divide your job into single pieces. And with this, I think I want to stop and give room to questions. Maybe there were some slides that I went through too quickly, but please remember that I will be happy to answer any questions if you contact me later in the next days. I can share links to articles. And finally, I want to thank High School for inviting me, and Giovanni, my co-founder, and Federico, who is a data scientist, was an enthusiast in Earth observation data, and they both helped me reviewing the slides. And also for the content, I've stolen from Pierre-Philippe Mathieu, who is the leader at Lab, and Robin Cole, who are all sharing material online.
So thank you, Chiara, so much. I really also appreciate your last sentence when you said that if you want to develop something with AI, some software, you need to do it by this, especially in this moment where we have a huge development and a lot of things happening week by week. One need to really focus and understand what are not only dividing in pieces, but what are the good pieces to pick up. So thank you again. I see a lot of questions. At least I heard the sounds related to hands. So let's start with Johanna.
Hi, can you guys hear me?
Yes.
Okay, great. So thank you so much, Chiara. Really interesting talk. I had a question regarding the kind of programmable satellites that you brought up. So I'm not sure if I understood it correctly. So so maybe you can explain this a little bit more in depth, because in my mind, you're still kind of constrained by the hardware that is on the satellite, right? So
Yes.
if you have, I don't know, infrared satellites that won't, you can't change that once you launch the satellite, right? Or maybe I'm
No, absolutely, you're right. But it's the same, you are also constrained by the hardware on your smartphone, but that doesn't mean you cannot put interesting applications on different smartphones, right? So this is I think I'm sharing, the website of the challenge, and considering that, I think the enabler has been that they are now able to put computational power, so kind of a CPU, GPU. So the bigger improvement is the hardware that can now do computation on the edge, on the satellite. So given the constraints from the sensors, but also the enabler of the chip, what would you like to compute on the edge instead of sending the whole raw data to the Earth, and then the elaboration is being done on the Earth. For example, I don't remember if it's already a reality, because a lot of times I read of future things and they kind of overpromise. But one application is to just cut the clouds from the image and remove them and just send to the Earth the cleaned image. So you send less data, you save time, etc.
I see. Thank you.
Welcome. Another question?
Go, Vij. Unmute yourself.
Oh, okay. I was just thinking if someone else is in line. Thank you, Chiara, for that great talk. It was super interesting. I'm really interested in one of the slides you brought up where you were speaking about unsupervised pre-training. So have you done something like that? Because in almost all fields, that solve big problems, you don't have access to enough label data. So how do you deal with that?
So for the specific pre-training of those visual models, they have been using the well-known, the tested methods. For example, masked autoencoders. So they remove some parts of the image and they put it through an encoder, and then the decoder does the image.
The reconstruction.
Yeah, the reconstruction. So that was for computer vision. While in my specific field, working with climate change or observing natural catastrophes, probably the most used method is clustering because we want to collect a set of features that we think are we can find different clusters that lead to different outcomes. So yeah, we can identify some patterns because probably in some applications, such as natural catastrophes, you are dealing with an anomaly detection kind of problem. It has an imbalanced data set, and you have a lot of the negatives and just a small set of positives. So yeah, these are more or less the challenges.
Thank you.
I have another question, if I can. It's just an opinion from your side. Do you think that running a space startup in Italy is particularly challenging? Because I know that lately there have been a lot of space startups like ICO, Genus, Studio Map. So is it having these competitors is something, I don't know, that you have to deal with, or
Well,
what's
thank
the
you for
story
the
there?
question. It's a good question, and before entering the startup space, I was just a data scientist, a tech person. I wouldn't have known what to say, but I tell you a couple of things. So first, the space startups can be divided into upstream and downstream. So upstream are the startups that are preparing some hardware like satellites to be launched. And now I don't want to say the wrong names. But some of the startups, some of the Italian startups are doing upstream, so they are kind of collaborating with this CubeSat initiative, etc. So the field of downstream is the field that relates to Eoliann, because we take the data from already existing satellites. We don't deal with hardware, and we just deal with the data. And the fact that there are already other players is kind of encouraging, because it means it's like you never open a bar or a restaurant in a street where there are no open bar and restaurant, because it means that there are no customers there. But you should not open when there are too many, because then you would be missed in the mix.
Sure, makes sense.
So I mean, also I think it's a very act of we are kind of proud of bringing Italian technology and entrepreneurship a bit forward, because as you know, ESA space Lab is in Frascati in Rome. I mean, it's very close to high school. So there is a lot of know-how, and yeah, I know you wanted an opinion, so maybe I gave you an opinion that I am quite content, and yeah, I'm happy with the Italian environment. It's not the most mature one, but yeah, why not?
We're pretty great.
We have time for a very last question, if any.
I mean, if nobody else has has a question, maybe I have another one.
Yeah, go ahead.
So I don't know, maybe just like a fun question, so to say. Is there any, I don't know, some like really cool project or like really cool customer solution? What's like your favorite thing that you've done so far? I'm not sure if you have like NDAs and if you can share, but like maybe.
Mm. Mm. Well, yeah, I think given that we are quite young, we're still dealing with a limited number of building blocks and projects, but for example, I can tell you that when we started the idea for the startup, we thought our main customer would be insurances, and then we found out banks wanted a similar type of data, but then you find out that they they want it a bit different. Like the banks are interested in assessing the risk for their, for example, mortgages, and they need to provide data to the regulator in Europe because they want to avoid things like Swiss bank being acquired or the SVB in US, all those problems. While insurances have been building in-house models, so they might want to treat your data as another feature, numerical feature for their models, or even other companies that are not insurance, like yeah, maybe I don't share, but other companies want our model like a black box that provides numerical data to improve their own models, while banks want our as a kind of categorical output, which they don't use for their models. They will use it for the reporting. So I think when you find out that you are just dealing with numbers, but then you will have to put them in a format that would be the best for your customer, that is another skill set. It's like no more a work for a data scientist, but you have to collaborate with your product manager and people dealing with your clients. And in a startup, a lot of people are working very closely. It's not like you have to communicate with the other 100 people department like in a big company.
I have a last question to ask. Since you are you're leading an AI startup, I'd be very interested to know how you keep up with the latest advancements in AI, because things are moving very fast. So
Yeah. I mean, you don't have time for everything. Like I order dinner instead of cooking sometime. But jokes apart, you need to have a curious mindset and maybe set some specific times for some stuff. Like I have halfway a community of other people working with AI and the observation where Cristiano is invited. But then in my company we do learning, we call it learning club, reading club, where everyone can present a paper once a week or once every 2 weeks, depending. And this initiative actually I've been doing also in my previous companies since I was in the startup in 2019. So if you can share your findings or read papers with other people, they will keep you accountable. While if it was only for you, maybe you would scroll Twitter. I used to scroll Twitter. Now Twitter is not the best. You will scroll LinkedIn, and sometimes even if you can read the abstract, that's cool. But if you are accountable with other friends and are getting motivated, it's better.
thank you so much.
Okay, thank you. Yes, this is really challenging to simultaneously be focused and keep yourself updated. I think it's one of the most difficult challenges for every AI scientist now. Okay, thank you again so much, Chiara. And I maybe next time I will invite you again for another talk, or as a mentor if we will have some challenge related to again to Earth observation. By the way, we are working on one challenge in Earth observation. I will talk about it to you later on. And that's all. Okay.
Thank you very much to everyone who attended. Thank you for your questions, and don't worry. Feel free to reach out if I didn't explain properly. I hope it was useful somehow.